shorter but same level of quirkiness. So try not to confuse them.
Yep. Okay. My name is Shane Keneally, and I am at the University of Illinois, and I'm taking over to give Casey a short break from speaking for a little bit. I'm going to cover the next couple steps, and we'll just see how far we get until the day's over. And as always, if you have any questions, please feel free to interrupt me and ask them. So in the last few steps, we built a coefficient diffusion kernel. So just the diffusion equation with diffusion coefficient. And now we're going to start looking at how we apply that to a more physical problem, in this case, Poisson's equation. Okay. So instead of passing our constant parameters to coefficient diffusion, which again you saw in the kernel that Casey built in front of you, we're going to start using the material system in Moose. And this allows us to apply properties that can vary in space. So if you remember in the coefficient diffusion kernel, we were inputting a parameter from the input file, right? We said coefficient equals 1 or 2 or whatever. The material system will allow us to add a much more complicated coefficient. So if it's some kind of equation that varies in space or even in time, we can input it through there. So with that said, I'm going to cover the basics of the material system. So in its basic form, the material system creates a producer-consumer relationship among objects. And what this means is that materials produce, its output is a thing called properties. And other Moose objects, including other materials, can consume these properties. So each property must be declared to be available for use by kernels. I'll show you what this means later. And what that, here's the pointer. In the kernel, instead of saying add param, you can declare the property here, which declares the material property and returns a writable reference. If you want to compute all the declared properties in your material at once, you can override compute QP properties. And you can use these, it can use coupled variables in kernels. So it works. So as I said before, objects consume material properties. So inside the object, instead of saying get param, you can say get material property of type, so real vector value, whatever value it is, in a kernel, or so as needed. It's not just computed at the beginning of a time step and stored. It's computed every single time it's required. The values are not stored between time steps unless they're declared as stateful properties. So inside the material class, you can declare property old or older, and this will tell it to store that requires the old value of the variable. You can tell it to use the old value of the variable using this. And I think we're going into more detail about that in a minute. So one important thing is that default values for material properties can be assigned within the valid params function. So if you don't actually value, so the program will still run even if you're not inputting one manually. So yeah, I just said that. Only real values may have defaults though, not vector values. So in some cases, you might want to output the material properties thing under the material that you're creating. In this case, we're creating, this is built into Moose. It's a generic constant material. So this creates two material properties, mat1 and mat2. And both of those are defined as having values of 1 and 2. And both of these materials have more complicated materials in general. So the outputs that we declared in the material parameter, it has several different formats. You can say all, so it enables outputting of all possible outputs, I've only used types, real vector value, and real tensor value. So it is possible to limit which properties are written to the output for each material using the output properties parameter. For example, if we just set output parameters equals mat1 from the previous material we wrote, it's only going to output mat1 class in Moose. So if you want more information, there's you can see all the tests in the materials in Moose. We're just scratching the surface here. I don't think I need to show that. Okay. So material properties can be of arbitrary C++ that support automatic output. So what's being done here is we're using an auxiliary kernel to read the material property and output it. Corey, I believe, will go into auxiliary kernels later. So you don't really need to worry about what that's doing at the moment. The point of and this is what I mentioned earlier, stateful material properties. So you can store multiple time levels of your material properties. You can also do this with variables. So in Moose, these are called stateful material properties rather than state variables. The only thing to keep in mind if you do this, take more memory. If you have a very small problem, this does not matter at all. But if you can imagine when you have multiple dimensions and a very complicated material or lots of material properties, this could start to become a problem. Okay, so with that said, I'm going to show you how we actually use a material property applied to a more physical example. So for fusion example. So we're going to create a material object called, very creatively, example material. Though for this example, the relative permittivity will remain constant. This could be applied to have some kind of spatially varying permittivity. So this is just a very simple example material. A very generic material header file. You can see here we're inheriting from material.h, and all we're doing is we're overriding compute QP properties, and we're declaring. And then in the C file, we're again reading from the example material.h file that I just showed you. There are no input parameters, and here is where we're declaring our material property. So this is saying we're creating a property called diffusivity, or we're here, this is where compute QP properties is created. And all we're doing is not even an equation, just an assignment. We're assigning the value of 1.01 to our material property diffusivity. So you can imagine here, you could add some parameters, you could couple in some variables and have some kind of calculated from a material property rather than writing it explicitly in your kernel. Of course, that would make the Jacobian more complicated because you need to compute the derivative inside the material as well, but just as an example. I don't see what this is. Oh, this is just the example mat diffusion header file. So previously, so it's essentially the same thing, except instead of writing an input parameter, we're coupling in the material that we just created. Yeah, and you can see here, this is the kernel's header file, by the way. So here, so in the C file, right here, input parameters equals diffusion. There's nothing changes there. And here in the constructor, we have diffusivity. We can call that whatever you want, but we're getting a material property that creates a material property called diffusivity. This will throw an error because it's going to look for a material property called diffusivity. So if you don't create that material, it'll break and it'll throw an error because it's looking for a material property that doesn't exist. And I will show you an example of the input file in a moment. So here's our residual statement. Again, materials can exist on the mesh. They can be spatially varying. We have to include the quadrature point here. And otherwise, the rest is exactly the same as before. I can see some blank faces, so if none of this makes sense, please let me know, or if you want clarification. Okay. So this is the input file. Just to give you an example, our new example matte diffusion kernel that we just built, the variable is v, and instead of adding a parameter from the input file, this example is going to read in a material property from our material. The body force does not matter for this example. So we have our two boundary conditions. On the left, we're assigning a constant value of 100, and on the right, example material, and of type example material. So if I go back to the source code for example material here. Oh, I went too far. Here we go. So this is going to just call this class, and all it does is, again, creates a material property called diffusivity and gives it a value of 1.01. Okay, and the rest is a Newton-Krylov, same PETSI options. And an example here is shown in step 3 of the tutorial app. So I'll run that really quick to give you an example. That is very choppy.
And try to center it on the page.
Yeah.
Or no, the text on
So I'll just go out to projects and show you where I'm going. So I'm going to the tutorial app. And step 3, materials in there. And that's it. It runs very quickly. I have already opened the pair view file. So if any of you need to see how I'm plotting this again, I can. But all it's doing is, again, we have one variable, v, and this is just behaves exactly as we would expect. Are there any questions about that? Okay. So with that said, we've created a very simple Poisson equation solver. I skipped over that because I was talking about materials. So we have a second kernel here, which is called the body force. I did not add that, but it's, yes. What equation is that solving? This kernel here?
Oh, that's just the rho, the e over epsilon naught times rho.
Okay.
Or
Yeah.
e times, it's rho over epsilon naught, I mean. They're just given some token values for
Okay.
the difference between
Yeah.
positive and negative.
Yeah.
space in your calculation, right?
Yes.
What if, for some reason, I'm interested in looking at an interface? Like, how do I imagine I need some sort of reference point. How do I tell the program that x equals 3 and start to begin the interface of the new material?
Yeah, so once you start adding different, you would split through the mesh, you would split your problem into different blocks. So block 0 is some domain, and block 1 is your other domain. And then you can tell this material, you'd add a under type here. You'd say block equals 0. And that would tell it exists on this part of the material, or this part of the, getting into a more advanced topic. But yeah, in general, you define the block through whatever mesh generator you're using, and then you can also have that under variables. If you just want Poisson equation in one domain, you'd say v equals block 1, block 0, whatever.
You could when we were talking about meshes. So normally if you just create blocks, they're given numbers, but then you can give them human readable names. So if you wanted water and air, then you could do water and air and say limit, like I only want to solve for v in air, maybe, or I only want to solve for this other thing in water. So that would be, yeah. So it's not just numbers. You can make them however you need to make it readable. Just for the example, it's just uniform in space. It's just a mathematical example. Yeah.
Any other questions?
So the Shannon Lab organization, that tutorial repository, all of that code is in that application.
Yeah. Directory, tutorial, this is the tutorial app that Casey was talking about. Tests, and I just ran step 3 materials here. But all of these kernels also exist, either in Moose or in the source and include directories in this tutorial. Okay, if there are no more questions, I'll move on to transient analysis. Okay. So now it was a very simple example, but we've shown how you can solve Poisson's equation and start looking at a transient problem. So for the case we're talking about here, which is trying to solve some kind of plasma system, if we have some applied voltage that varies over time, you're going to start wanting to use a transient analysis. So for example, in this case, we're going to have an applied voltage, assign executioner to perform a transient solve rather than a steady state solve. So I'm going to go into a little more detail about executioners here. So as I just said, there are 2 main types of executioners, steady and transient. Moose provides a number of built-in executioners, but it's built to be modular, so you can modify this as needed. So steady state executioners generally solve the nonlinear system match to approve the solution. So there are a number of options that exist in the executioner block. So we can define the linear tolerance. So this is when you run the input file, you see the linear solve steps. So this sets the tolerance on those solves. We can set the nonlinear relative tolerance or absolute tolerance, and the max number of nonlinear iterations, which is default to 50. And I think in all the examples we've shown here, it's only taken 3 nonlinear iterations to solve. So transient executioners solve the nonlinear system at least once per time step. So to input a couple more options, you need to give it a time step, which is a starting time step size, the number of time steps, or alternatively, the start and end time. So you can give a time in realistic units, if you'd like, and a scheme, which is the time integration scheme. One useful option is steady state detection. So in your execution, you can also tell it to only check after a certain number of time steps if you'd like. So this is useful because if it's steady state, you don't need to run anymore. It'll just stop the problem and print out the problem has achieved steady state. Okay. So Moose provides the following implicit time integrators. The default is backward Euler and diagonally implicit Runge-Kutta method, and a couple explicit time integrators, which I've never used, so I do not know how well those work. So each one of these supports adaptive time stepping, which means that as the simulation will run, it will try to increase the time step. So it'll do this automatically unless you explicitly tell it to not do this. Okay, so if we want to run a transient problem, we need to add an additional kernel to our problem, namely the time derivative. So adding time dependence to a steady diffusion equation can be as easy as just adding the time derivative kernel. These are very straightforward. It's just the derivative of your variable with respect to time. And it turns out this simply because you can interchange the order of differentiation and summation. So in the equation on the previous slide, du dt is the time derivative of the kth finite element coefficient of the following form for the time derivative, where constants a and b depend on delta t and the time stepping method. Okay, and then from that analysis, you can get the Jacobian term for your time derivative, which is just the coefficient a times phi u in moose. So a time derivative kernel in your compute QP residual block, you'll have simply this, your test function times u dot. And moose automatically knows that this is the derivative du. Any questions about that? Okay. Yeah. It's essentially the derivative of the variable with respect to the variable, at least in the Galerkin scheme that we're using. Okay, if you need to provide a coefficient for the transient term, you can say your compute QP residual Jacobian term, as we did for the coefficient diffusion kernel that we built earlier. Okay, and the following code can be found in the Moose repository under example 6 _ transient. If you installed Moose, you have this already in the Moose directory. So this is an example time derivative, and we're also inheriting from material. And we've added a time coefficient parameter with a default value of 1. So if we use this kernel in the input file and do not add a parameter, it will automatically assume 1 for the time coefficient. Okay, and then we have the time coefficient in the compute QP residual slot. We're computing the time derivative. Since we inherited from the time derivative kernel, we can use the exact same compute QP residual from there. And we're just multiplying that by, if you recall. And the Jacobian does not change because our time coefficient is a constant value in this case. Okay, so in order to create or convert your problem to a transient problem, you need to add your appropriate time derivative kernels. So your time step, the scheme you're using, by default it'll be implicit Euler, so you don't necessarily need to specify a scheme if you don't want to, and either a number of time steps or start and end time, and that will run the problem in transient. And the next couple slides are just going to show you the convergence rates of those different time integrals being run. It's just a time derivative. It's a time-dependent diffusion problem with a source term f. And f is chosen so that the exact solution is shown here. Okay. That is a little blurry, but you have the slides available to you in the tutorial directory if you can't read this. On the left are the implicit schemes, and on the right are the explicit time integration schemes. And if you have no questions about that, I'll keep moving forward. Okay. So you can modify the way your problem is solved in transient. So this is very simple. It's easier than extending the transient class if all you want to do is provide a custom method for choosing which time step you want to use. So you don't necessarily have to create your own transient kernels if this is the case. So there are several different built-in time steppers. Constant DT, this function time step, so this will change the time step depending on whatever function you give it. So as you can add just a explicitly written function, and that will calculate the time step. I do not know what the other ones do because I have not used them, to be perfectly honest.
Post-processor DT take current Friedrichs lags limit. So that can be computed as a post-processor, and then you can feed it into your time stepper, so you're not crossing the stability limit. So that would be that. And DT2, that'll solve for DT, and that'll predict the next DT you will be solving for. So it's an adaptive time stepping scheme. And time sequence, I believe, reads the DT from a CSV file.
Okay. Yeah. Zapdos in particular, which is the increase your time step as the simulation runs, as I was talking about earlier, and then if it ever runs into a problem, it'll step back a little bit and try to converge there. So you can start with a very small time step. By the end, you could be taking huge time steps if the problem is stable at that point. So those are very useful for making your simulation run in a reasonable amount of time. Time step, obviously, it'll increase by a fixed amount until it reaches a user-specified minimum value. Oh, and this is the DT2 time stepper. Nice. So in this case, this is exactly what he was talking about. So you take one time step at size DT, and then you take the right time step through that method. So I'm going to skip through that. Yeah, and time sequence stepper provides a vector of time points using parameter time sequence. So time sequence stepper just moves through these time points. So as he was saying, you can have a number of time steps in an externally provided file, and it'll just run the problem at those specified. We can add a time-varying applied voltage with a parsed function, which all that does will write our function as a function of time, and the moose will be able to read that. And a function Dirichlet BC, which same as I showed previously. We have our example mat diffusion with a variable v, and we're reading our diffusivity or permittivity from the material that we created. The same boundary condition on the right, value 0, but on the left, we're using function that we've called function or voltage wave. And on the next slide, here is our function. So we're using a function called voltage wave, which is what we read into the boundary condition in the previous slide. This is a parsed function with a value shown here. So if you remember from our original problem on the left side of the boundary. And the only other difference here is our executioner block. So we're setting it to a transient problem. Our time step, we're setting a specific time step here. We're setting an end time. So these are in actual seconds units. We're also setting a nonlinear relative tolerance here. Yeah, when in doubt, things usually are just 0. Okay, so since we used a new boundary condition in this example, the Dirichlet boundary condition shown, function Dirichlet boundary condition, I'll take this opportunity to talk about the different boundary condition systems we have in Moose. So as Casey showed earlier, a boundary condition, similarly to kernels, We have a compute QP residual, compute QP Jacobian. We can input parameters. We can input couple variables. We can use material properties. Or actually, we can't use material properties, can we, on boundaries? We can? Okay. We can use material properties on boundaries. Yeah, please. Integrating or multiplying by the test function and integrating. Your residual statement will be what that creates, right? The Jacobian is essentially the derivative of that residual with respect to all the variables in the system. Yeah. Should I go into more detail? Integrated over the boundary. So instead, they just specify values on the boundaries. In this case, that means a Dirichlet boundary condition. Boundary conditions which are integrated over the boundary inherit from integrated boundary conditions, and non-integrated boundary conditions inherit from nodal BC. So those are all classes that are built into Moose. Conditions, again, it's very similar to what's available to kernels. So we have u, which is the variable, and the gradient of u, phi and gradient of phi. We can have the test functions, and again, the gradient of test functions. QP, or the quadrature thing that is not, is the boundary ID. So this is the, when we set up the boundary condition, we said left or right, or top or bottom. That essentially tells it which boundary is being applied to. So that's what we're setting, the boundary ID. Okay. So the coupling of values and gradients, oh, was there a question? Nope, okay. The coupling of value, coupled value old, so this is the stateful properties that I discussed earlier. We can couple in the gradients of variables, or the coupled dot, which is the coupled time derivative of a variable if we need to. So to go over Dirichlet BCs, this just sets a condition on the value of the variable on the boundary. So these are usually not integrated. They're just on the boundary, and therefore this is the residual, or almost. We need to integrate it still. Integrated boundary conditions, including the Neumann boundary conditions, are integrated over the external face of an element. So their residuals look similar, are very similar to kernels. So in this, if our dot product here, the gradient of u dot the unit vector is 0, then the boundary integral is 0. So this is known as the natural boundary condition. So this is the default Neumann boundary condition. We also have periodic boundary conditions in Moose. So it supports periodic boundary conditions fully through 1D and 3D. It includes support for mesh adaptivity, and it can be restricted to specific variables. And I think that is good enough for that. So here is an example of a periodic boundary condition. So variable u, direction to supply the coordinate direction, directions to wrap. And as an advanced usage, you can specify a translation or transform function. Okay. So with that said, I'm going to start going into the actual fluid equations. So now that we have a handle on custom kernels and steady and transient analysis, we have enough knowledge to start tackling the electron fluid equation. So to simulate fluid equations for the ions and electrons, we need to build a couple more things. We have our time derivative term, our particle diffusion term, coefficient diffusion, and reaction terms. We could use reaction in Moose like we did for the example, but we'd need to modify it in order to use an actual input reaction rate coefficient, constant, or function instead of just assuming a value of 1. So after we do these, we are going to be manufacturing a solution to make sure all of this is working properly. So we'll start with the fluid equations for the electrons. So here, the dot product of the gradient with the flux and our source term here, which is our reaction kernel. And our flux is given by our diffusion term and our advection term. So here, K is the reaction rate coefficient. In this case, we're considering it to be ground state ionization. N, which is right here, is our back. So the only thing we need to add, or add from scratch at least, is our field advection. So to add our field advection term, we need to add a coupled kernel that couples a variable into the density. So the residual contribution from this term would simply be this term shown here. So since the sign for this term changes, so I will sit down for this. Shown here is the header file for the field advection kernel that we're creating from scratch here. So the only difference you'll notice, or one of the biggest differences you'll notice, is here we have our compute QP off-diagonal Jacobian. We need this because we're coupling with respect to all the variables you're going to have off-diagonal Jacobian terms in the problem. We're declaring a real property called mobility, a real property called sign, which I discussed in the previous slide, and unsigned int potential ID, and I'll show you how this is applied later. This is for the off-diagonal E-field advection, or the class E-field advection. Here, we're adding our required coupled variable, potential. So from the input file, you'll add potential equals whatever you called your potential variable. In this case, we called it V, I believe. We also have our, if you remember from the equation, we actually need the gradient of the potential, or the electric field. Okay, so here's our residual term shown at the top here. We have sign times mobility times our variable u times the gradient of the potential, and have phi here instead of u. But then it becomes a little more complicated when we take the derivative of the residual with respect to our potential variable, because that's now contributing to the off-diagonal Jacobian term. So what this is saying is if we are looking at an index that corresponds to our potential ID it's going to be 0. So here it's converting grad potential to grad phi, shown here. Does that make sense to everyone? I know I went through that pretty quickly.
So why is the Jacobian of when you're trying to do a transient, right? You said that is 0, right?
0 only if your kernel is not acting on the variable u. So in this case, if we have a reaction term, for example, and all it's doing is coupling in a different variable, so it's just a source term that doesn't depend on the variable it's actually providing a source to, then the diagonal term would be 0. So the derivative of the residual with respect to u is not 0. So we have an on-diagonal Jacobian term here. This is just the advection step. This is, so here. In this equation, this is only this part right here, grad dot this. That's it. All of this into one kernel, but that makes your application very hard to use.
You would still keep the time derivative part separately because it's a time kernel.
Yeah.
Just a regular kernel.
Yeah.
So in that case, you could put every other term other than the time derivative term in one kernel with one residual and one Jacobian. It would make the determination of that Jacobian given. Or am I mistaken?
No, in this case, we're calculating it through Poisson's equation.
Okay, so that's what the question was. You need the Jacobian with respect to V with the given such.
Yeah, if it's just given, if it's just a value, it does not contribute to the Jacobian. You're correct.
And for testing purposes, you can give your kernel as a parameter a number or something that it as a coupled variable that has a solution, even if Moose will just treat it as an input, and it allows you to decouple parts of your code to test chunks without having to worry about coupling for just the test.
So moving forward, just keep in mind, when we say kernel, that means one specific term in our PDE. So ideally, each kernel will tackle an individual term in our problem. Let's get back. Okay, so this is the last thing we talked about. So the next thing we need is our ground state ionization to have a constant material property, K, which is our rate coefficient. And we're also coupling in a variable mean En, which means mean energy, stands for mean energy in this case. So this is the C file. So we're adding a required coupled variable, second species, our second species density, which is defined as the coupled value. K, our rate coefficient, is being fetched from a material property that we're defining as Ki. And we will show how this residual, or what this residual looks like here. So our compute QP residual statement times U. So in this case, we don't actually use mean En.
This is in this case, your K here is going to be defined as a constant. So if you were to say, if this is argon and you wanted to use like a rate coefficient equation, then dependence on mean energy or a dependence on electron temperature. So in this case, this Jacobian, if you have a material property that is a function, your Jacobian would actually be kind of complicated here. But for the sake of simplicity, and not A times second species density times phi, but that's just a typo. But if you had a K that was mean energy dependent as well, then you would have another off-diagonal Jacobian contribution like the previous one, and you would have to take into account the exact form of your Jacobian. It's just there was a typo.
So in this case, our rate coefficient is just going to be a parameter, not a complicated function. So as we'll talk about later in this workshop, it is generally important to manufacture an artificial test for smaller parts of a code to test right-hand and a custom right-hand side term that forces the problem to converge to a predetermined solution. This allows you to make sure that everything is working properly because you know the solution is supposed to converge to. And in this case, we have designed the solution to this problem to be that function shown on the bottom here. So this is our input file. And in this case, we're actually running in steady state again for the purposes of this. Is our electron density. Scaling, this is something that you have not seen before. This is sometimes needed for convergence. What this does is if our electron density is on the order of 10 to the 13 in the solver, like the Newton solver or preconditioned Jacobian-free solver, this will scale the problem back by this factor. So we've added a couple auxiliary variables, which will be talked about later. So these are being used to compare this is the potential method of manufactured solutions and electron density. So this is the values that we're comparing to. And again, these are the auxiliary being computed that we can use to compare our solution to in this case. So here we have our kernels. We have our electron diffusion term, which is just coefficient diffusion with a diffusion coefficient listed here. The E-field advection term, which we just built. We're inputting a mobility of 3 times 10 to the state ionization electrons. So this is, we're just adding a parameter of second species and giving it a density of 3.22 times 10 to the 16, and this is meant to be the background gas density that is being ionized to produce electrons. And our mean energy, which is not used, is 4 in this case. And this is the same boundary conditions as before. On both sides, we have Dirichlet boundary conditions of 1,000 and 1,000. This is for the electron density, remember, not the potential. And here we are defining our functions. So our potential function is shown here. I'm not going to read off a function, which is a parse function. So these are essentially, this is the manufactured solution. So these are what we are trying to compare to. And here we have our generic constant material. This is what's inputting the material property Ki into the ground state ionization kernel. If you remember, we said we're getting a material property called Ki, and this is where we're defining it here. Okay, and here, like I said, we're back to doing a study problem for at least this test case. And this is in the tutorials directory, again, under the tests, and this is step 5. So if you'd like to run it yourself. Here we go. So I'm going to go to the step 05 fluid equations. Nonlinear convergence solves. This is a study problem, not a transient one. Okay, step 5, we'll load our Exodus file. And I'm just going to plot the data. I used a keyboard. In the top right, you'll see the legend. So green, which you cannot see, is the calculated electron density. And then we also have our auxiliary variables, electron density underscore MMS, which stands for method of manufactured solutions, and our potential. I mean, they're both calculated from Moose. It's just that one is calculated from the nonlinear solver, and one is given an analytic function. Yeah. So in this case, the electron density profile is this. Yeah, the pair view. Okay.
Because I tend to be overcautious about such things. I create manufactured solutions when I've added a lot of new code, even if I'm not necessarily coupling it to things. In this case, we've kind of isolated this particular problem, and we're making a solution for it to test all the kernels. So yeah, you could make another manufactured solution for coupled cases and do a similar function, and do that. So yeah, you can if you wanted to do it that way too. No, so we will tomorrow. We'll ask. And so, in short, when you're doing something like that, you're trying to pick a solution that stretches the legs of the problem. So something that might be physically reasonable, like in terms of shape, or in terms of like maybe it has a steep gradient, so you want to like capture that and make sure your physics can kind of quadratic function as the solution we're going for. But then I'll calculate so that nasty. Could you go back one slide? So that nasty function, RHS func. So if you take your solution, so say the any profile func there, if I plug that in to each term in the strong form of the function, what comes out the other side is that nasty mess right there. And so then you add that term into your equation, So the right-hand side becomes 0 again, and then it forces the solution to be. And then the boundary conditions are dictated by the profile function you've provided. So they're Dirichlet now or Neumann, depending on how you're manufacturing it. But about it a little bit more in detail tomorrow. But I wanted to introduce it just a little bit early, maybe. So, anyway. So does anybody have any other questions? Okay. So since we're at the end of this section, how about take a really, really short break, like 5 minutes, 10 minutes. Actually, let's do 10 minutes, and then